Hello everybody, and now you might be wondering, if you are solving some kind of differential equation and have some kind of initial conditions, what's the best way to put in your limits? Or, is it better to put the limits directly into the integral, or is it better to just write a plus c and find the plus c? So I want to take you through this and hopefully convince you that putting the limits directly into the integrals when you integrate is actually much easier than integrating it first, then writing your plus c. I think this is actually best demonstrated by an example. So the example we're going to use today is the radioactive, the formula for radioactive decay. So this looks like this. So we have dN by dt is equal to minus lambda times n. Now, where does this formula come from and what's this all about? Well, dN by dt is the rate of change of the number of radioactive particles in a sample. So let's say you had n at some time. So n will be a function of time because the number of radioactive particles will change with time as the particles decay. And basically we're saying that it's proportional to the number that are left. So the higher the number of particles that are left, the faster they will decay. Or rather, the rate of change of the number of particles left will be proportional to that. And the negative sign is there because the number of particles will go down with time because n is positive, this constant is positive, so the gradient of n as a function of time will go down because the number of particles are going down because particles are being lost due to them undergoing radioactive decay. And this constant is known as the decay constant, and it's there because simply we have a proportionality relationship and we don't know what else to do. So we're going to solve this differential equation, and we're going to have the initial condition that at t equals 0 we have n being equal to n naught. And a more takes up less space. It's more It's more concise to simply write n of 0. So n when t equals 0 is equal to n naught. Okay, now let's solve this differential equation. Using separation of variables, we can solve this. So we can write integral of dn. Now, if we take that n to the other side, we get over n is equal to minus lambda times the integral dt. And of course, I've just taken the minus lambda out of the integral because it's a constant. Now, I'm going to show you the first method, which is probably more familiar to you, which is taking the antiderivatives and then doing a plus c and then working out what the plus c is. So let's do that first. Now this is going to be equal to the log, the natural log, which I'll just denote log, of the modulus of n. And this bit will be equal to, well, this will be the integral of 1 dt, which is t. So this will be minus lambda times t. And we can just put a plus c there because actually you might have a plus c times by minus lambda, but then a constant times minus lambda is also a constant. So this is perfectly valid. Right, so we can now use our initial condition to find what c is. So at t equals 0, n equals n naught. So we can put 0 into here and put n naught into here, and then we can solve for c. So we can write log of n naught is equal to minus lambda times 0 plus c. So c is just equal to log of n naught, and we can put that back into the formula above. And we get that, this is log modulus n naught, and of course we can put the logarithm onto that side. We can subtract logarithms, which means we can combine the logarithms, and actually when you subtract it, I won't go through the details because I think anyone who's watching this will know what to do, but pretty much you can do that, and then you can take the exponents of both sides, and we get n over n naught is equal to e to the minus lambda t. And indeed, therefore, n of t is equal to n naught times e to the minus lambda t. Okay, and that's our solution, subject to these initial conditions. Okay, So now I want to run you through the method that we would use if we were to put the limits directly into the integrals. Or rather, sorry, put the initial conditions directly into the limits of the integrals. So let's go back. We know that this is the solution we expect, so I'm just going to leave that on the board. And let's do this using the limits. Now, the way you put the initial conditions into the limits is by choosing one of the limits. Usually it's conventional to choose the lower limit. In fact, in my entire life I've only ever used the lower limit for this. So you can just do the same if you feel comfortable with that, or you can do it with up one if you prefer. So you evaluate the lower limit at t equals 0. Okay, now what you say is, at t equals 0, what is the lower limit of n? What is n equal to at t equals 0? Well, at t equals 0, n is n naught. So I'm going to put n naught, n equal n naught, in my limit here. On my dt, again, I put the value of t when t equals 0. So the value of t at t equals 0 is 0. So I can just put t equal to 0 here. And on the upper limit, you just integrate as if you were doing an antiderivative. So you just put your general n as a function of time. So essentially we're just saying when t is some general t, and at a general t, n will be n of t, and t will just be t. Okay, so now we can evaluate this, these in indefinite integrals, and we get log mod of n, where n goes from n naught to n of t, is equal to minus lambda t between t equals 0 and t. Now we can evaluate these, so we get log mod n minus, and I'm just dropping the function notation there, we know that that's n of t, minus log of modulus of n naught is equal to minus lambda t minus 0. So we get minus lambda times t there. And indeed, again, we can combine the logarithms. So we get log of n over n naught is equal to this. And again, if you take exponents of both sides, then you get this equation. And you return the solution that we had when we took the plus c. So hopefully I've convinced you that this is actually a useful method. And it is a method which will actually lead to the same answer regardless of if you do the plus c or if you do the limits. I would argue that doing the limits is faster because you're not having to go like, oh, okay, plug it in, c, blah, 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 solve for c, put c back into it, and then solve the equation. With this, you're kind of like taking the fast lane to just directly solving the equation. So I think this is better. And as you saw in my integration the equations of motion video for the gravitational attraction problem, you saw that actually by putting the limits directly in, I was able to write the integral in terms of a different function. So actually, when you put the limits in, it allows you to unlock different areas of mathematics which you otherwise wouldn't have been able to use if you took the antiderivative and then put in plus c. Now, you still may be slightly confused with this, and I'm just going to go through another example. For example, when t isn't equal to 0, just to consolidate and so that this works no matter what. So, let us say that instead of t equals 0, n is equal to n naught, let's say we know the value of the number when t equals 10. Okay? So let's say instead of t equals 0, our condition, our known condition is that at t equals 10, n is equal to n 10, say. And we can just modify that in this form by saying that n of 10 should be equal to n10. And this is our fixed condition of the problem. Now again, we can go ahead and separate variables, integrate again. Oops, that's not the case. We do integral dt. And once again, we can just take the antiderivatives, put in the plus c, so we get log of mod n is equal to minus lambda times t plus c. T equals 10, n equals n10, so we get that log of n10 is equal to minus lambda of 10 plus constant. So we get the constant is equal to lambda 10 times lambda plus log modulus of n10. Okay, and putting it back into there, we get log 10 times lambda plus log of n10. Now remember, this n10 is just a fixed number. It could be 1,000, it could be 10 to the power of 23, it could be whatever you like. It's just the number of particles when t equals 10. Okay, so we can now rearrange this to get n of t. If we put the logarithm on that side, we get log of n over n10 mod is equal to, now the lambdas will factor out, so we get minus lambda t minus 10. And I think with the minus cancel to give a plus, so I think you can convince yourself that's true. And when you take the exponent of this, you get n of t is equal to n10 multiplied by e to the minus lambda times t minus 10. And indeed, when you put t equal to 10 in here, then this becomes 0, you get e to the 0, and indeed n of 10 will be equal to n10. Okay, so now I'm just going to prove to you that when you do it in the fashion of limits, then you will get the same thing. So I'm just going to go ahead, rub this off. And so if we were now putting in the limits, now this time we're concerned with t equals 10. So this is our known value. So this is what I'm going to put as the lower limit. So the lower limit, I'm going to evaluate everything when t is 10. So when t is 10, n is equal to n10. So I'm just going to write the lower limit on this integral will be n equal to n10. And on the upper limit, I'm just going to put n of t. General, or upper limit will be when t is equal to t. So that will just be n of t. Here, the lower limit is when t equals 10. So we say that t is equal to 10 here. And on the upper limit, we just do it as a general t. We can now solve these definite integrals. So we get log of, now I think you're capable of knowing that this will give you log n, and then you do log of that minus log of that, so it gives you log n over n10 is equal to, well, here we get minus lambda times by, well, this gives you a t evaluated at t and then subtract 10. So we get t minus 10. And then again, we can take exponents of both sides. We get that n over n naught is equal to e to this. So when then multiply both sides by n10, you get n of t is equal to n10 e to the minus lambda t minus 10. So you can use either method. You can do a plus c and then work out plus c, or you can do the limit trick, just evaluate the lower limit at a specific value at which you know, evaluate the upper limit at the general n of t, general functions, general time t, that you at some random time, and they both lead to the same answer. So I hope I've convinced you that this limit thing is indeed useful, and thank you for watching.